Now we'll look at the problems in the sixth assignment. The very first problem, it's a regular non-inverting amplifier, except that the op-amp has an input resistance which is 1 kilo ohm, which looks like it's a very low value. Okay, so essentially all we have to do is connect up this part, that is we have Vi connected here, the feedback is from there, and we have 9 kilo ohms and 1 kilo ohm. And what you're asked to find is Rn. So you have to, so let's say we have Vtest, or maybe I'll still call it Vi, and I have to find the current that goes in there. Okay. So that is In, and Vi by In gives the input resistance. Okay. So how do I go about doing this? You can choose any variables you want, but if you say this is In, then this voltage is In times 1 kilo ohms, and the output voltage, which is 1 million times Vd, is In times 1 kilo ohms times 10 to the 6. Okay. Then you have to write Kirchhoff's current law at this node. Okay. The current through this, which is In, plus the current here, which is, remember, this voltage is at Vi minus In times 1 kilo ohm. Okay, because the voltage drop here is In times 1 kilo ohms. So the current through this is In times 1 kilo ohm times 10 to the 6, that's the output voltage, minus the voltage here, which is Vi, plus In times 1 kilo ohm, okay, divided by 9 kilo ohm, and the whole thing equals this voltage Vi minus In times 1 kilo ohm divided by 1 kilo ohm. Okay, and you can solve for In with this, and you take the ratio Vi by In, which is the input resistance, and you're asked to specify this in mega ohm. If you calculate it correctly, you will find that this is about 100 mega ohm. Okay. Now, why does this happen? I mean, it looks like the op-amp itself had a very poor input resistance, whereas the negative feedback with a very high gain increases it by a very large amount, and you have a very high input resistance. So 100 mega ohms is quite respectable. The current flowing in will be very small. So this is why the main feature of a negative feedback system, or the main characteristic required from an op-amp when it's used in negative feedback, is high gain. Okay, we need as high a gain as possible. Now, its input resistance and output resistance usually are also cited. You want high input resistance and low output resistance and so on, but these are kind of bonuses. If you have a very high gain, then you don't need any of those things. If you don't have infinite gain, then having a high resistance helps somewhat, but the main thing is to have a very high gain, because you can see that 1 kilo ohm input resistance, which looks like a very low input resistance for an op-amp, actually still causes only 100 mega ohm input resistance in the circuit, because it gets multiplied by effectively the loop gain, which is 10 to the 6 divided by 10. Okay, and here is another similar problem. In this case, the op-amp has an output resistance of 10 kilo ohm, which again looks very poor. Okay, because the load that is connected to it also has 10 kilo ohm, but it has a gain of 10 to the 6. Okay, so to calculate the output resistance, you ground the input, you set the input to 0, and I'll draw the rest of the circuit. Normally, when the resistance that you connect is the same as the output resistance, it looks like performance will be very poor, but now we'll see what happens. Okay, and let's say we apply a test voltage Vtest here. Now, because you have Vtest connected here, across this you get V test by 10. Okay. So this voltage here, Vd by the way, is minus V test by 10. So this voltage here will be 10 to the 6 times Vd, which is minus 10 to the 5 times V test. Okay. So what is the total current that flows here? Into this you have V test by 10 kilo ohms, and into this you have the voltage across this is basically on this side. On the right side we have V test, on the left side we have minus 10 to the 5 V test. So this current is V test times 1 plus 10 to the 5 divided by 10 kilo ohms. Okay, so the total current is V test times 1 plus 10 to the 5 by 10 kilo ohms plus V test by 10 kilo ohms. And you can calculate the exact value, but you can see that the most dominant term is this one. Okay, so this is approximately V test times 10 to the 5 by 10 kilo ohms. Okay, so this is the current. The resistance, which is the ratio of voltage to current, will come out to be 10 kilo ohm by 10 to the 5 or 0.1 ohm. Okay, so the answer is supposed to be in ohms, so it's 0.1 ohm. Again, because of high gain, you get a very small output resistance as you would like from a voltage controlled voltage source. Okay, so the output resistance is low mainly because of feedback and having a very high gain in feedback. Okay, not because the inherent output resistance of this is small. In this case it's not small, but it becomes very small because of this gain of 10 to the 6. Okay. Now this one you're asked for V0 by II. I mean, these things we have actually derived the formula for in the lectures. So it's a matter of substituting the formula, and then of course you have to derive the parameters of M1. But with the 200 microamperes of current, you know that this corresponds to 200 microsiemens of transconductance. Okay. So you'll find that the answer is Rs times Gm Rg RL minus RL divided by Gm Rs RL plus Rs plus RL plus Rg. Okay. Now if Gm tends to infinity, then this term will dominate and this term will dominate, and you will get V0 by I exactly equals Rg. In this case, this Gm is not infinity, so you have to substitute basically Rs, which is 250 kilo ohms. I will not write the units here, I will use kilo ohms and millisiemens. Gm is 0.2, Rg is 50, RL is 200. Okay, and similarly in the denominator you'll have 0.2 times 250 times 200 plus Rs, which is 250, RL, which is 200 plus 50. Okay, and this, if you simplify, 0.2 times 50 is 10, so you get 2000 minus 200, 250 times 1800, and in the denominator you will get, this is 50, 50 times 200 is 10,000. Okay, and all of these rest will be 500, so this is 10,500. So if you calculate it, finally you will get this to be 42.9 kilo ohms. Okay, it should have been 50 kilo ohms. If Gm was infinity, it would be 50 kilo ohms, but because Gm is finite, it is slightly less. It is 42.9 kilo ohms. Okay, and Rn, so Rn is measured here, and again this we have calculated the formula for. It is Rg plus RL by 1 plus GMRL, which is 250 kilo ohm by 1 plus 0.2 times 200, because RL is 200 kilo ohms, which is 250 kilo ohms by 41, okay, which works out to about 6.1 kilo ohms, okay. And R out, which is looking that way, again has a sort of symmetrical formula. R out will be Rs plus Rg by 1 plus GMRS, which is 300 kilo ohm divided 1 plus 0.2 millisiemens times 250 kilo ohms, which is 300 kilo ohms by 51, which will give you about 5.9 kilo ohms, okay. This question asks for the swing limits. Basically, you need to find when the transistor goes into triode region, and the next question is about cutoff. For both of these things, we need to know the value of VGS of M1 so that you can calculate the drain current as well as the swing at the gate, okay. Using circuit analysis, just like you calculated V0, you can also calculate VGS. It turns out that VGS is minus Vi times Rs Rg plus RL divided by Gm Rs RL plus Rg plus RL plus Rs, okay, and this is minus 5.95 Vi for the given values of components, okay. Now we also know that VO is, we've already calculated this, (42.9) times II, okay. So the total quantity VDS equals the quiescent voltage 3 volts plus 42.9 times II, and the total quantity VGS is the quiescent voltage, which is also 3 volts, minus 5.95 times II, okay. We have to make sure that VDS is greater than VGS minus VT, or when it just enters the triode region, VDS equals VGS minus VT, okay. And if you solve for this, you will find that 3 volts plus 42.9 II equals 3 volts minus 5.95 II minus VT. II equals minus VT divided by 42.9 plus 5.95, and substituting VT equals 1 volt, we'll get II equals minus 20 microampere. It's somewhere between minus 20 and minus 21 microamperes. And the value of II when M1 just cuts off, the total drain current ID is 200 microamperes plus Gm times VGS, which is minus 200 microsiemens times VGS, which happens to be 5.95 II. With this 5.95, the units are kilo ohms, okay. And you set this to 0 for cutoff, you will get II to be 200 microamperes divided by 200 microsiemens times 5.95 kilo ohms, which gives you 168 microampere, okay. So if you get somewhere between 167 and 169 microampere, that is acceptable, okay. Now this is another circuit, and you are again asked something related to the swing limit when M1 enters triode region, okay. and all the capacitors are shorts and so on. So Vi appears directly at the gate. There is no series resistance. Okay, so the incremental voltage here is Vi. Now I won't draw the small signal picture, but I'll do it directly. The voltage here is Vi times, in fact from this point to here it is like a source follower. Okay, so Vi times GMRL, which is 0.2 millisiemens times 45 kilo ohms divided by 1 plus 0.2 millisiemens times 45 kilo ohms, which is basically 9/10 of Vi. And the incremental drain current is Vi times Gm divided by 1 plus GMR, which is 0.2 millisiemens times 45 kilo ohms, or basically 20 microsiemens times Vi. Okay, and this drain voltage here incrementally is this current going into 100 kilo ohms, because L2 is an open circuit. So the voltage here is minus 20 microsiemens times Vi times 100 kilo ohms. Okay, which basically gives you minus 2 Vi. Those are the incremental voltages. The total voltage at the gate is the DC voltage, which you can easily see is 9.5 volts, and the total voltage includes the increment Vi, and the total voltage here is, you can see that the operating point voltage here is 16 volts because the inductor is a short at 16 volts minus 2 Vi. And for M1 to just enter triode region, Vd must be equal to Vg minus Vt. In other words, 16 volts minus 2 Vi should be equal to 9.5 volts plus Vi minus 1, or 3 Vi is 16 volts minus 9.5 volts plus 1 volt. Okay, or in other words, Vi is 7.5 volts divided by 3, which is equal to 2.5 volts. Okay, so when Vi is plus 2.5 volts, this would have increased, this would have fallen, and the transistor just enters triode region. The next one is Vi at which M1 just cuts off. We know that the quiescent value is 200 microamperes, and to that we have 20 microsiemens times Vi of increment, and when this equals 0, Vi is minus 200 microamperes by 20 microsiemens, or minus 10 volts. Okay. Now the last question, it relates to when M0 enters triode region. By the way, in this case, if this current source is ideal, then this voltage can keep falling. But because this is also a transistor, when it falls below a certain value, this enters triode region. M0 enters triode region. What is that value? Again, we have to find the total voltage here. The total voltage there is the operating point voltage, which is the operating point voltage at the gate minus the operating point gate source voltage, which happens to be 6.5 volts. And we already know what the incremental voltage here is, that is 0.9 times Vi, and this has to be greater than Vgs of M0, which you can easily calculate to be 3 volts, minus Vt, which is 1 volt. Okay, so M0 just enters triode region when this is an equality, or Vi equals 2 volts minus 6.5 volts divided by 0.9, or 5 volts. Okay, the answer is minus 5 volts. Okay, so we calculated the upper swing limit of this that is when M1 enters triode region, and that is 2.5 volts. We can also calculate the lower swing limit by assuming that this current source is ideal. Then M1 cuts off when Vi is minus 10 volts. But that's not really the swing limit, because when Vi is minus 5 volts, M0 enters triode region, and we cannot make Vi any more negative without driving the transistor into severe nonlinearity. Okay. So the swing limits are really, the upper swing limit is plus 2.5 and the lower swing limit is minus 5 volts. Okay.